last topic in this unit on thermochemistry deals with standard enthalpies of formation. The standard enthalpy of formation is a characteristic property of a chemical compound. Every chemical compound has its own value of the standard enthalpy of formation. Delta H is enthalpy change, sub F refers to formation. The superscript 0, sometimes pronounced naught, refers to everything being in their standard states. So what is the standard enthalpy of formation? It is the enthalpy change for the reaction in which 1 mole of the compound is formed from its constituent elements in their standard states, meaning the states in which they exist, both physical states and molecular forms, at 1 atmosphere pressure and 298 Kelvin, which is standard conditions. Okay? For an example, let's write an equation for which the enthalpy change is equal to the standard enthalpy of formation of methanol. When you see a question like this, what you are writing is a chemical equation that shows 1 mole of the compound being formed, so there's only a single product with a coefficient of 1, from the elements that make it up in their standard states. So let's begin first by writing methanol. CH3OH liquid. And on the reactant side, I'm going to list all of the elements that make it up in a balanced form. So I'll have 1 mole of carbon. Graphite, it turns out, is the standard state of carbon, plus 2 moles of hydrogen gas, because under standard conditions, hydrogen as a diatomic molecule exists as a gas, plus half a mole of O2 gas. Okay? And the value of the standard enthalpy change of methanol is negative 239 kilojoules per mole. Now, that does not mean that I can do this. You probably can't take 1 mole of carbon, 2 moles of hydrogen, and half a mole of oxygen, and in one magical step make a mole of methanol. Okay? But again, it doesn't matter because of Hess's law. If you could carry out this reaction, this is what the enthalpy change would be. So let's practice that. For each of the following, write a balanced chemical equation for which the enthalpy change is the standard enthalpy of formation of the substance indicated. So you can start by simply writing the formula of the product. Solid aluminum oxide, what makes that up would be 2 moles of aluminum metal plus 3/2 moles of O2 gas. Liquid chlorobenzene, C6H5Cl, that would be 6 moles of solid carbon plus 5/2 moles of H2 gas plus 1/2 mole of Cl2 gas. Solid ammonium nitrate, again, 1 mole of the product. That would be 1 mole of nitrogen gas plus 2 moles of hydrogen gas plus 3/2 moles of O2 gas. Okay? So, the question is, why is knowing standard enthalpy of formation values of chemical compounds useful? Well, this is huge. It's because you can use them to calculate the enthalpy change for any reaction that involves those compounds. If you take any chemical reaction, whether you actually carry it out or not, and you know the standard enthalpy of formation of each compound in the reaction, you can calculate the enthalpy change for that reaction. Okay? Let's take an example of combustion of methane. Okay? 1 mole of methane reacts with 2 moles of oxygen gas to form 1 mole of carbon dioxide gas and 2 moles of liquid water. Okay? Hess's law says that the enthalpy change is independent of the pathway. So we're going to make up an imaginary fictitious pathway. And that pathway is very simple. We will take the reactants, we will convert them into their elements in their standard states. We will then take those elements in their standard states and let them react to form the products. Here's a picture from the textbook that illustrates this. So I've got 1 mole of methane gas and 2 moles of oxygen, which are the reactants. I'm going to break the methane down into 1 mole of carbon and 2 moles of hydrogen, which are the elements of the standard states. The 2 moles of O2 remain unchanged. And then in the second step, I'm going to take 1 mole of carbon and 2 moles of oxygen to form 1 mole of carbon dioxide, 2 moles of hydrogen, and the remaining mole of oxygen to form 2 moles of water. So the question is, how do I use the standard enthalpies of formation of the compounds in this equation to calculate the enthalpy change? Okay? Well, here's how it is. Reactants to elements to products. If I decompose 1 mole of methane to its elements in their standard states, the enthalpy change for that process is the negative of the standard enthalpy of formation of methane. 2O2 to 2O2 has an enthalpy change of 0, obviously. The standard enthalpy of formation of carbon dioxide gas is the enthalpy change for 1 mole of carbon plus 1 mole of oxygen forming 1 mole of CO2. And 2 moles of hydrogen plus 1 mole of O2 forming 2 moles of liquid water is 2 times the standard enthalpy of formation of water. Okay? what I see now is that if I cancel what appears on both sides, carbon and carbon, hydrogen and hydrogen, oxygen and oxygen, what I get is CH4 plus 2 O2 gas forming CO2 gas plus 2 H2O liquid. And if I add up the enthalpy changes in the right-hand column, what I get is the following. Delta H equals the standard enthalpy of formation of carbon dioxide plus 2 times the standard enthalpy of formation of liquid water minus the standard enthalpy of formation of methane gas. Okay? You may have noticed in the back of your book, these are tabulated, and if I look them up, I get these values. Negative 393.5, negative 286.4, and that gives me an overall enthalpy change of negative 891 kilojoules per mole. Okay? So let's do some examples. Before I get to that, so here's the general formula. You can see it in sort of a very specific way here, because in this problem, I have the standard enthalpy of formation of the two products minus the standard enthalpy of formation of the one reactant that's not a pure element. So the general formula looks like this. The enthalpy change for reaction is equal to the sum, remember capital sigma means sum, of the standard enthalpies of formation of each of the products multiplied by their stoichiometric coefficient minus the sum of the standard enthalpies of formation of each of the reactants multiplied by its coefficients. Okay? So let's do an example of the problem. The reusable booster rockets of the space shuttle used a mixture of aluminum and ammonium perchlorate as fuel. Possible reaction is as follows. Calculate the standard enthalpy change for this reaction using standard enthalpies of formation. You will see posted in the SIS topics box, as well as in the back of the textbook, a table of standard enthalpies of formation, which are quite useful. So I'm going to begin by writing this out in the most general form. The enthalpy change for this reaction is standard enthalpy of formation of aluminum oxide plus the standard enthalpy of formation of aluminum chloride plus 3 times the standard enthalpy of formation of nitrogen monoxide gas plus 6 times the standard enthalpy of formation of water vapor, make sure you get the correct physical state, minus the standard enthalpy of formation of ammonium perchlorate. We leave out aluminum because it is a pure element in its standard state, and therefore, by definition, its standard enthalpy of formation is 0. I'll plug in my values with units, negative 1676 kilojoules per mole, plus negative 704 kilojoules per mole, plus 3 times positive 90 kilojoules per mole, plus 6 times negative 242 kilojoules per mole, minus negative 295 kilojoules per mole. These are all taken from the table of standard enthalpies of formation at the back of the book, which gives me a value equal to negative 3,267 kilojoules per mole of reaction for the standard enthalpy change for this reaction. Now, you may be asking yourself, where do standard enthalpies of formation come from? Well, if you cannot carry out the reaction in a calorimeter, then you can't measure the enthalpy change. You do it indirectly by calculation. I mentioned in an earlier video that measuring enthalpies of combustion is really easy, and in fact, that is where we get most standard enthalpies of formation, is by burning stuff and measuring how much heat is given off. Here's an example of how that works. The standard enthalpy of combustion of butane gas to form carbon dioxide and liquid water is given there. Per mole of butane, use this fact plus the standard enthalpies of formation of the products to calculate the standard enthalpy of formation of butane. So our first step, obviously, is to write and balance an equation. So butane, C4H10 gas. Combustion involves reaction with oxygen to form carbon dioxide and water. And we're going to use water in the liquid phase here. Okay. To balance that, I will put a 4 before carbon dioxide and a 5 before water. That gives me 8 plus 5 is 13 oxygen atoms on the product side. You may be tempted to multiply everything by 2 so that you don't have a fractional coefficient, but pay attention. The problem says negative 2,878 kilojoules per mole of butane. So the negative 2,878 kilojoules applies to this reaction when butane has a coefficient of 1. Okay? If you were to balance it by putting a coefficient of 2, you would have to double that, but it's perfectly fine to use a fractional coefficient here anyway. Okay? So, using the equation, I'll write out the general form. The standard enthalpy of combustion is 4 times the standard enthalpy of formation of butane. I'm sorry, that's not correct, carbon dioxide. Plus 5 times the standard enthalpy of formation of liquid water minus the standard enthalpy of formation of butane. So to rearrange that, I get the standard enthalpy of formation of butane equals 4 times the standard enthalpy of formation of carbon dioxide plus 5 times the standard enthalpy of formation of liquid water minus the standard enthalpy of combustion that we're given in the problem. So this is equal to 4 times negative 393.5 kilojoules per mole plus 5 times negative 286 kilojoules per mole minus negative 2,878 kilojoules per mole. Pay attention to signs. And we get that the standard enthalpy of formation of butane gas is equal to negative 126 kilojoules per mole. Even though it's almost impossible to form butane gas from its elements in their standard states and measure the enthalpy change, we're able to calculate the enthalpy change using Hess's law. That's pretty much chapter 6.